Hello, today I am presenting our paper, Accelerating Online Reinforcement Learning via Supervisory Safety Systems. This paper was prepared as a collaboration between the University of Stellenbosch in South Africa and the University of Pennsylvania in the United States of America. The authors are myself, Benjamin Evans, Johannes Betz, Hongre Zeng, Herman Engelbrecht, Rahul Mangaram, and Hendrik Jordan. The problem we approach in this paper is the online training of deep reinforcement learning agents for robotic systems. The current dominant approach is to train DRL agents in simulation and transfer the trained policies to the physical vehicle. This method is severely limited by the sim-to-real problem, which is caused by the difference between the simulator and physical vehicle dynamics. The sim-to-real problem causes the agent to perform worse in reality than in the simulator, posing a safety risk and making it difficult to apply DRL agents to physical platforms. We propose using a supervisor to enable the online training of DRL agents. While some supervisors have been used for this purpose, current methods are limited by simplistic or impractical supervisors. Examples include simple linear systems, using a human supervisor to take over, or simply reversing if the vehicle is near a wall. Other approaches have tried to use reachability theory, but this requires a lot of real-time computation, which is a limited resource on board embedded systems. We propose a novel supervisory safety system to train a DRL agent online a physical vehicle. Our supervisor operates using a three-step process of 1. Using a dynamics model to calculate the next state, 2. Checking to see if the next state is safe, and 3. If the next state is unsafe, using a pure pursuit controller instead of the agent. We use the single-track bicycle model to simulate the agent's action and calculate the next state. We use a viability kernel, which is a list of safe states for a given map, to check if the next state is in a safe region or not. If the next state is not safe, we use a pure pursuit controller that follows the center line and thus will always move the agent back into the safe region. We reformulate the learning to take the supervisor into account. Conventionally, episodes are defined from when the agent started until the vehicle crashed or completed a lap. Using our framework, the agent never crashes and always completes laps. Therefore, we redefine episodes to run from the initial state until the supervisor intervenes. When the supervisor intervenes, the agent receives a penalty to train it to drive safely, independent of the supervisor. We evaluate our method for the task of driving a physical F1/10 scale car around a track. We demonstrate that our supervisor can train a DRL agent to drive autonomously on board the vehicle with no prior training. The top left graph shows the actions selected by the agent in green and the actions implemented by the supervisor in blue. In the beginning, the agent selects many random actions, but as the training progresses, the agent learns to select fewer unsafe actions. The bottom graph shows the reward earned by the agent for each 20 planning steps. The graph shows that within 800 steps, the agent has learned not to require the supervisor, demonstrating excellent sample efficiency. We compare the agent trained on board the vehicle to the baseline agent trained in simulation and transferred to the car. The top right image shows the trajectories taken by the two different agents. The red trajectory is the baseline, and it is seen that it is very squiggly with the vehicle swerving a lot. The blue trajectory is our method, using the supervisory safety system, which is a lot smoother. This result is reinforced in the numerical results, which show that our method presents an improvement in lap time, distance, mean steering angle, and total curvature. We conclude that our method is effective for training DRL agents on board physical vehicles, with excellent sample efficiency and improved performance. Online training improves the usefulness of deep reinforcement learning agents for the application on physical robotics. Future work should focus on extending the supervisory methodology to other high-performance robotic systems.